So far we've covered in detail the exponential distribution, the Weibull distribution, and the gamma distribution. We now take on the subject of other lifetime distributions here in section 4.5. There are a number of distributions out there that are very flexible in terms of their modeling, and they include some shapes that don't occur quite that often for the hazard functions, such as the upside down bathtub or the bathtub shaped hazard functions. The parameters will generally be denoted in this section by a, b, and mu. Scale parameters will usually be denoted by lambda and sigma. And finally, shape parameters will be generally denoted by kappa, gamma, and delta. All of the distributions that you're about to see will have support from 0 to infinity, except the uniform and the Pareto distributions, and we will stop when we get to those. So here are some one-parameter distributions. One should be very familiar by now, which is the exponential distribution. A second one-parameter distribution is the Muth distribution. I don't believe it gets used very often. The exponential distribution, however, gets used often and typically for electrical components. Here are the two-parameter distributions. The first is the Weibull, and we've gone through it in detail. And you can see we have the probability density function, survivor function, hazard function, and cumulative hazard function for each of these distributions. The second on the list there is the gamma distribution. You can see once again with the gamma distribution, one of its downsides here is that the incomplete gamma function is used to determine the survivor function. Now the uniform distribution seldom gets used, and the reason it seldom gets used is its support runs from the constants a to b, and most lifetime distributions do not cut off in that fashion, so it does not get a lot of use. The next one is the log normal distribution. You can see a fair amount of intractability here because for the survivor, hazard, and cumulative hazard functions, I'm just writing down their definitions or taking them from the 5x5 matrix, and that's because the probability density function does not integrate easily. Finally, down at the bottom is the log logistic distribution, and this is a nice distribution in that you get tractable density, survivor, hazard, and cumulative hazard functions. So if I were to take this list and say what distribution gets used the most often in reliability, I would put the Weibull distribution at rank 1. Probably the log logistic gets used the second most, and then the log normal gets used next. One thing interesting though about the log normal is this is the first one we've encountered that actually has that upside down bathtub shaped hazard function. Here's some more two-parameter distributions that are defined on t greater than 0 with the exception of the Pareto. The first is the inverse Gaussian distribution, and you see it has parameters lambda and mu, not very tractable survivor, hazard, or cumulative hazard functions. Exponential power is an interesting distribution in that it is the first distribution we've encountered that can actually take on that bathtub-shaped hazard function. And even better, the lifetime distribution representations are pretty tractable for the exponential power distribution. The next is the Pareto distribution, and this one has a support on t greater than or equal to lambda rather than the usual t greater than or equal to 0. It has very tractable lifetime distribution relationships. The Gompertz distribution is used quite often in actuarial science to model the lifetime of either a person or a commodity such as a uh, automobile or a boat or a motorcycle or the like. This takes us to three parameter distributions. And the first is the Makeham distribution, and that is used in actuarial science. This one's kind of clever. IDB, and what that stands for, increasing, decreasing, and bathtub. So this function right here, that's the hazard function, that thing can increase, or it can decrease, or it can take on a bathtub shape. So it's a very flexible distribution. And finally, here is the generalized Pareto. In addition, there is the three-parameter generalized gamma distribution, which was put together by Stacy in 1962. That showed up in Annals of Mathematical Statistics. And that particular distribution includes the Weibull as a special case, the gamma as a special case, and the log normal as a special case. In addition, some of the families of distributions, there is the Johnson system, the Burr system, and the Pearson system. Some of those systems of distributions are possible for lifetime models. Now, we have not hit all of the lifetime models that are out there. Andy Glenn put together the arctangent distribution. Lane Land put together a logistic exponential distribution. There is another known as the Birnbaum-Saunders fatigue life distribution that shows up from time to time. So there's a number of other distributions that are out there. Finally, the last thing is to look at two distributions which are known as n-parameter distributions, and they are related to the exponential distribution. One of these is called the hypo-exponential distribution, and the other one is called the hyper-exponential distribution. The hypo-exponential distribution falls in the IFR class, and here's the way it works. If t sub I is exponential with parameter lambda sub I. Now notice that all of these lambdas do not have to be the same here. Then when that's true, their sum has the hypo-exponential distribution. And when all of those parameters happen to be the same, this collapses to the Erlang distribution. That's one that falls in the IFR class. Then the other side of the coin is the hyper-exponential distribution. It falls in the DFR class, and its assumptions are the same. And that is, if t sub I is exponential with parameter lambda I, and that's for I equals 1 to n, and then t has this particular probability density function where the p sub i's are positive constants and they sum to 1, so you may recognize this as a mixture distribution. That one is known as the hyper-exponential distribution, and it collapses to the exponential distribution with failure rate lambda when all of those parameters lambda 1 through lambda n are equal.